Hi, this is part 3 of ECE 141 Lecture 9, Practical Considerations in Digital Transmission. So now we're going to be studying the effect of ISI using what we call the eye diagram. So let's say we have a pulse-shaped signal S of t. So let's say it's easily a square wave. And at matched filtering, we assume matched filtering, then the recovered symbol looks like this. Okay. The red one is the S1 of t, and S2 of t is the green one. So this should be S2. Anyway, so it looks like an eye opening if we superimpose the two plots at the same time. Okay. So if we have this sequence of symbols transmitted, the corresponding output would look like this. Okay. Suppose we put it in an oscilloscope. Okay. And the oscilloscope is triggered at the sampling rate. So at the sampling rate, it will display, if it's triggered by the sampling rate, it will display something like this. Then it will display the next one, which is this. And it will display the next one right here, becomes this. And so on and so forth. The display in the oscilloscope will look like this. Okay, you get what we call the eye pattern of your constellation. Okay, the wider eye means your signal or your transmitted signal has a better noise immunity. Okay, so this is the point where we want to sample our signal. Right? If we're using maximum likelihood detection, then the boundary between the two symbols are in between in the optimum sampling point is in between them, right here. Okay. And you have a distortion at the optimum sampling point. Okay. You have a noise margin at the timing jitter, and the slope here shows the sensitivity to the sampling time, and so on and so forth. Okay. If you have a higher modulation order, then the number of traces in the eye actually increases. For example, your 4PAM will look like this. Now, we assumed that the pulse here is a square wave, or a rectangular pulse rather. If it's a raised cosine pulse, it will look something like this. It looks more of an eye, right? When there's noise, it becomes noisy, and you have less immunity. So the opening in your eyes are actually smaller. So sampling must be done at the time instant when the eye is large enough. Okay. The problem is, how do we time that properly? So we need to be able to recover the timing so that we know when to sample. So there are different algorithms to recover our symbols, or the timing of our symbols rather. One example is the early-late gate synchronization. So every symbol period, you need 3 samples. Okay? You need 3 samples. The correct timing is when it's when your eye is balanced. Okay. What does that mean? The timing error is 0 if the 2 samples between your middle sample is approximately equal. Okay. If your timing is late, then the difference between the 2 samples here is not 0. Therefore, you have a timing error. Okay. If it's early, then the difference again will be, there will again be a difference between the 2 samples right here, between your supposed sampling period. Okay. So the timing error is computed as such: the middle multiplied to the difference between this minus this. If the timing error is greater than 0, then we have a timing advance. It means we timed too early and we need to adjust accordingly. Okay. So if it's late, okay, then the timing error is 0. Now, this simple timing recovery scheme right here works well for binary signals but less effective when we have multiple level signaling. Right? Because if you have multiple levels, then your delta K will become proportional to the level of your symbols. Right? So it would always adjust accordingly. Anyway, the next is Gardner's method. It requires two samples per symbol and a knowledge of the previous symbol timing. Okay. So if you have two samples per symbol, then let's look at two symbols that were transmitted. So this is symbol 1 and this is symbol 2. Okay. The correct timing is when the sample between them is approximately 0. Okay. Late timing is when there's some value of the sample between the two sampled symbols, and early also if there's some value. So to compute the timing error, this formula is used. The symbol in between multiplied by the difference between the two symbols. Okay. So if the symbol in between them is 0, so if the symbol in between is 0, then the timing error is approximately 0. If it's less than 0, then you have your timing is advanced. If it's greater than 0, then your timing is delayed. For 2D constellation, you apply the method separately on the in-phase and its quadrature components. Okay. Finally, we have the M&M algorithm, Mueller and Müller algorithm. Okay. The parameter is different from the previous two. So the timing parameter or the timing error is basically the current sample, yk, multiplied by the detected symbol in the previous one, okay, minus the previous sample multiplied by the current detected symbol. Okay? So basically, if you sample too early, your delta K will become greater than 0. Okay? If you sample too late, your delta K becomes less than 0. So you just need to be able to observe, just need to mix and match basically your current symbol and your current sample, okay? Your current sample and your current symbol, and compute the timing parameter. The best thing about M&M algorithm is that it only needs one sample per symbol to be able to extract the timing information. So as compared to your early-late synchronization, you need 3 samples per symbol. For this, you need 2 samples per symbol, and for this, it's 1 sample per symbol. Okay? So the underlying principle is you sample when the eye is wide open, and I discussed this earlier. So to compensate for the error, you need to adjust the sample clock correctly, where your delta K right here for all 3 algorithms, not just M&M, indicates the size of the error. And the algorithm should be dynamic and should run continuously to compensate for your small clock variations and noise. Right? So an extension of M&M algorithm can be realized for two-dimensional signals by using conjugates. Okay. Right. So the next problem when transmitting signals over, for example, wirelessly, is when we have frequency shifts. Okay. So to be able to transmit wirelessly, you need to be able to shift your frequency at a very high value so that your antennas will become practical. So how do we recover our signals to baseband when we shift our signals in high frequency? Right? So the best way is to just multiply a cosine, because we cannot realize a complex sinusoid in the real world. However, it's wasteful of spectrum. The resulting signal becomes this. So aside from attenuation, so you see the original signal is attenuated and then split into 2, and there is an image information that will become useless right here. And the only useful information is basically the upper bands right here and right here. Okay, so there's wasted spectrum in these two holes right here. There you go. There's redundant information and waste of spectrum. That's why we have quadrature modulation. So you recall your complex baseband signals right here. Okay, we can transmit them using a cosine carrier and a sine carrier, your in phase and your quadrature component. Because of this, your redundant information from here and here disappears. Right? So how does the quadrature modulation work? Consider first a signal that is baseband. It has this magnitude spectrum and this phase spectrum. And then we use what we call the Hilbert transform to get a quadrature of this, a quadrature version of this baseband spectrum. By using the Hilbert transform, if you get the Fourier transform of the Hilbert transform, basically its frequency spectrum is multiplied by negative j in the positive frequency and positive j in the negative frequencies. So what would happen to the spectrum of your, from this, it will become this spectrum right here. Now, to shift our frequency, recall we use IQ modulation. One is multiplied by a cosine component, one is multiplied by a sine component. Okay, and basically the cosine component is multiplied to the original signal, and the sine component is multiplied to the Hilbert transformed signal right here. And you'll get these two spectra. If we add them, as you can see here, they have the same phase, but the magnitude is negative on the other side, as you can see here. Same phase spectrum, but negative, a part of the magnitude spectrum becomes negative. If we add them, then you get your original signals. Okay? So the addition will result into these two, the red one right here, the dashed one if you get the difference. So the red one is the upper sideband and the dashed one is the lower sideband. And because of this system, we actually reduced the bandwidth requirements from just transmitting by shifting using a cosine component only. The drawback is your system becomes more complicated. So this IQ modulation increases system complexity but reduces the bandwidth by 1/2. The problem is when we downconvert them. How do we determine if the phase of our signal is how do we determine the phase of the local oscillator when we transmitted this signal right here at the receiver? We want to be able to have the same phase as our local oscillator so that our symbols won't be displaced. If you don't have the same phase, your 4PSK signal will become from this. If we don't have the same phase with the local oscillator at the transmitter, it will have a frequency shift like this. So from here to here, this is what we'll receive. That's why we need to recover the phase of the local oscillator to be able to correct our signal to become like this. Okay? So even if we know the frequency of the transmitter and phase of the transmitter, there's no guarantee that it will be the same at the receiver. So between the transmitter and your receiver, there could be a time delay, which creates a phase offset. In wireless communications, TX and RX can have frequency shifts due to Doppler phenomenon, and it always fluctuates due to noise. To recover the phase of our transmitter, we can use what we call the phase locked loop. So the phase locked loop is a control system. Right? The phase lock loop is a control system for a noisy carrier right here. There's going to be a loop filter that gets the cosine of the phase error. The cosine of the phase error will be injected into a voltage-controlled oscillator, which will then be fed back to your noisy carrier right here. At the end of this loop, you have this output right here, and because of the feedback, this theta E becomes approximately 0, and you get your original phase right here. Okay? So that's how you recover the phase of your transmitter. So this is the visualization of what will happen. This is the input sinusoid, and the signal from the PLL with your 90 degrees. You have a 90-degree phase shifter. You'll have this synchronization. Your input and your output will be synchronized or coherent after 5 microseconds. Okay? Another way to recover our phase information is to use what we call the Costas loop. In this case, it's a double Costas loop. Okay? Uh, the phase information will be recovered for both the in-phase and the quadrature component of your signal. Okay? So this is basically just two phase lock loops at different carriers. This is your double Costas loop. And at the end, you'll get your in-phase and your quadrature components. Okay? So Costas loop synchronization becomes this. If you don't have any Costas loop synchronization, your symbols will just keep spinning forever because of the frequency difference between the two local oscillators. Right? After the Costas loop, your symbols will now be recovered to its original state. Okay? So this is actually an example implementation that I did using the GNU radio. So GNU radio is a simulation platform, but can also be used for software-defined radio, actual hardware. Right? If you use timing and synchronization recovery, you get an overhead loss of data. Okay? But if you just continuously transmit the same thing over and over again, you'll eventually recover it. So in this case, I transmitted Mabuhay Pilipinas. Alright, so that is the end of lecture 9. Again, if you have any questions or comments, if you need any clarifications, do not hesitate to leave a comment in the comment section below. Thank you for listening. I'll see you next meeting.